Hokie dokie. Welcome to Working Out 1026 Lab 4 with me. I'm your lab partner, Joe Mama. Let's jump into it. So I have the iPad pulled up on here because it's a very draw on the graph, sketch situation. It's heavy with that stuff, and it's very minimal Excel usage stuff. So maybe that's a good thing, maybe that's a bad thing. I don't know. So we're gonna do a little bit of drawing, sketching, filling out charts, things like that. We'll see what we can get done. So jumping into it, we're doing a little bit with slope fields, which at this point you should have done like a week or two ago. I don't know, a little while ago. You've already been tested on it and so on. So I'll kind of skim through it as best I can while touching on all the important stuff. So the first thing, talking about slope fields, for example, y prime equals y minus t, the derivative of y, so the derivative of y prime represents the slope of the tangent line for the graph of some function y at any point t y. So y prime tells us the slope at any one location, and then they give us a bunch of examples, so hopefully we don't have to think about that because we've already delved into slope fields in the past. So they say, before you leave the presentation area, finish drawing the slope field. Draw on points 0, 0 to 1.5, 1.5. You can use Excel to help with your calculation. So they give us this whole layout of a chart here, and they ask us to find all the slopes or the y prime values for all these different t and y values. So this is, I think, the only thing I used Excel for. So what I did, I kind of finessed it. So you'll notice, sorry, this eraser is not the best. You'll notice that all the t values are 0, then they're 0.5, then 1, and then 1.5. So along the t column, I've done something like 4 zeros, 4 0.5s, 4 1s, and 4 1.5s. And then all the y values have sort of a repetitious behavior to them as well, right? So 0 to 1.5, 0 to 1.5, 0 to 1.5, 0 to 1.5. So we have 0 to 1.5 copy and pasted 1, 2, 3, and 4 times. So these pairs 0, 0, 0, 0, 0.5, and so on all the way down will give us all the slopes we need that they're asking for, I guess. So all we do is input all these t and y values. Then we click on C2 and we type in B2 minus A2. I know they say B2 minus A1. They also have a lot of other typos in this paragraph here, so please ignore those. Those are insane. I don't know who typed that up. So hit enter, on that formula there, and you'll just click and drag this down here, and you'll just get all the y prime values corresponding to these pairs, right? And so then they're asking you to put all those slopes in this chart. I'm not going to do that. You can see all the slopes right here corresponding to the pairs of t and y values. All right, I'm going to leave it at that. Let's keep going. They say fill in the slope table below to organize your calculations. So if you really wanted to, let's do a couple points. So for example, let's do 0.5 and 0.5. So let's start with that. 0.5 and 0.5 means on this chart down here, we're going to put a dot right at 0.5, 0.5, and then we're going to put a little tangent line, a little tick mark with the slope that's equal to this value here. So 0, slope of 0 at 0.5, 0.5. Let's do another random one. Let's do 1.5 and, I don't know, 0. 1.5 and 0 would take us, 1.5 out, but 0 up or down, so we're right on the x-axis, and we have a slope of negative 1.5, so a pretty steep-ish negative slope, right? So maybe something like, I don't know, that, roughly. I guess they don't have the arrows, so maybe just something that feels a little too steep, maybe, I don't know, something like that. Anyway, that's the idea. They're asking you to put all those slope lines at all these points that we found, but it's up to you if you want to do that. I'm not going to force anyone to do anything, but I'm not doing it. So now sketching solutions on slope fields. So now sketching slope fields by hand isn't difficult, but it's tedious. So then they give us another slope field. They say, remember that differential equations don't just have a single solution. They have a solution for every initial condition. So what they're saying is, like, you know, along all these slopes here, along all these paths, there's basically like an infinite number of solutions to this differential equation that they give you. And the solution, each individual solution is based upon the initial condition. The initial condition is just another phrase for the initial point that they give you. So, for example, if they gave you the initial point, like t equals 0 and y equals 1, you'd put a point on this graph at 0 and 1, and then the solution to the differential equation with this initial condition would follow this point, would follow these slope lines all the way down like this. And so you know that line I've just drawn is a solution to the differential equation. So let's see if we can get rid of this so you can read. What do we have? So the tangent line segments provide directions telling you how the solutions move across the plot. So again, they're just saying the slope lines, the line segments tell you how the solution moves. All right, let me stop talking myself into a hole. So they give you this fun website that you can, you know, practice getting slope fields with. So I think I just did the one that they were talking about here. Let's see if I can find it. Oh gosh, there we go. Alright, so this was something I was messing around with the other slope field, but this is the one they asked for. So you know, you can practice typing in y minus t times 2 times t, and then 0 2 0 2, and then you know you can get an image. And then I think the cool thing about this is that you can click on any initial point and it'll fill out the solution for you. So like you can click at say like 0.5 and 1, and you click right here and it'll fill out the solution that passes through that point using the slope field. So it's kind of cool if you want to play around with that. I'm pretty sure they ask you to kind of play around with it a little bit to kind of get used to it and understand what it's doing when you click on different points. So what do they say? The solution you see represents a function, yada yada. What is the initial condition of this point? So if they're talking about this one, the initial condition you could say is, you know, you're starting at 0 for the t value, but you're starting at 0.5 for the y value, right? At that point right there. So that's all there is to it. Try clicking on other initial conditions, yada yada. Get a good feel for how they, okay, yeah. Sketch and label the 3 specific solutions y of t to this differential equation. So here's a couple different ones here. Let's click around and see if we can see these while we use this applet here, or whatever you call it. Oh, I just got rid of it. That's cool. Okay, well, let's type it in again. What was it? Y minus 2 times t. And we got to change all these. Sorry about that. Pretty quick fix. Okay. Let's hit enter. I just wanted to like clear the graph really. So we have 0, 1. So we'll click 0, 1. Okay. And then 0.7. So we'll click 0.7, probably like right there-ish. A little below 0.75. I don't know. And then what's the other one? 0 and 0.4. So 0.4 would be, you know, down here a little bit. Okay. So then they say sketch and label. So like I guess they want you to actually like label them on here, I guess. Oh, I guess you didn't really need the, you know, solution. I think it was more of like like they wanted you to do it just roughly on this graph here. So, you know, you got something like that. That was real rough. Hold up, let's try that again. So it follows that down, and then 0.4 would do something like this. You get the idea. So that's the rough sketch, and they want you to label them. Hopefully you know which one's which. I'm not going to do that. Predator-prey, multiple differential equations in a phase plane. Let me make sure you can see these. Okay. So they say something about the system state at one time value is basically just like the H and L values at that time. So to ask or to say like what's the state at this time, that's just another way of saying what's the H and L value at that time. Okay. So they say use the graph above to find the state of the system, in other words the H and L values, at all these different times and fill in the chart below. So very tedious, but let's kind of talk through a few of them. don't think I'm going to do all of them. But so again, at 0.5, we want to know what's the H and what's the L value. So at 0.5, we're looking like right here. The H value is the solid dot. So like right here, we got about like, I don't know, 1.2, 1.25 maybe. And then the L value has got to just be, I don't know, barely over 5, if that. So I'd say like, what did we say for the first one? Was like 1.25. So you'd say 1.25, and then L was like, who knows, like 0.55, if that, maybe like 0.52. It's barely gone up. And then you would keep going through there. So let's do, I don't know, I'll like jump around. Let's do 1.5 and 2.5, I guess. So at 1.5, we're looking here, and maybe right at that max. So H, the solid line, would be maybe 1.7, and then L would be maybe like 0.9, 1.7, maybe 0.9, and then let's do one more, 2.5. We see that H starts to go back down, so it looks like it's kind of returned to where it was at 0.5, so maybe like 1.2-ish. And then at 2.5 for the L, it's almost at its max. So I'd say that's like 1.6, 1.7. Might do like a 1.65. You get the idea. So then once you have those, the idea is then, notice the difference between this graph and this graph here. They have T on the x-axis here, right? But down here, they have H and L's on the axes. So the idea is then to basically like use these H and L pairs as your new ordered pairs and plot those as points on here. So while we're at it with these 3 points I've just found, let's go and fill these in on this graph. So 1.25 on the H and 0.52. So I mean that's like right up here maybe. I might have gone a little too high. That's okay. So 1.7, 0.9, 1.7 and 0.9. We're looking like right here maybe. And then 1.2, 1.65. So 1.2, 1.65, we're like way up here. Interesting. So it's gone from here to here to here with each of those points. Now, I don't think the point is really to connect them like I just did, but in a way it kind of is, because as T gets larger, it kind of like shows the direction of things around the H and L little plots there. But that's all I'll do for these for now. Hopefully the idea makes sense enough for you to do it all on your own if you prefer. Let's keep rolling. Phase portrait. So turns out with a little work we can make a phase portrait just like a slope field. It'll be small tangent lines, but maybe the difference is just having arrows instead of just like, I mean, that had arrows too, so I would call that a phase portrait. They feel like the same thing, to be honest, but I think arrows are mainly the difference they're talking about. I don't know. Let's see. So they give us H prime and L prime. Okay. So they give us a point. They calculate an H prime and an L prime at that point. Okay, the tail of the arrow will be at this location, and the arrow will point in the directions given by the rate values of H prime and L prime that we calculate. Now, this whole thing, this box right here, it's a crazy typo. It's pretty awful. I don't know if it looks like this on yours or not, but what they're trying to say here is H prime dictates how many units left or right, and L prime dictates how many units up or down. So if H prime is positive, then the arrow will point to the right. If H prime is negative, the arrow will point to the left. And then likewise down here, if L prime is positive, the arrow will point up. If L prime is negative, down. The arrow will point down. So they ask you to, I guess, like fill in these values here, use Excel or a calculator. So I guess I could probably do this in Excel real quick. Yeah, why not? Let's do Excel. Alrighty, I'm back. So I didn't read this super thoroughly before I started this video. So I realized what we need to do with this chart here is, so they don't give you any equation or anything for H and L. They do give you the T values, and they say somehow you're plugging in H and L into these H prime and L prime equations. And so where these H and L values come from, they say, is from the previous page. Let me see. They say you've already found HL points on page 1, but you need to use them to calculate H prime and L prime. So I went ahead and filled out a few more, the main ones we needed. So 1, 2, 3, 4, and 5. Again, we saw we can identify the H and L points by looking at the H and L locations at different times, 1, 2, 3, 4, and 5 on this graph, and then you label them here. So then those become the H and L values that you use at those corresponding times, 1, 2, 3, 4, and 5. And so I've already transposed those into Excel here, so we can see. All right, where'd Excel go? Come on. All right, so let's get rid of this here. And so I put those points, these ordered pairs, in here, right? So now we're going to calculate H prime. So they say H prime right here is H minus H times L. So we'll do like equals H, which is this, minus H times L. So that, again, B2 times C2, or L. So then we have that, and then we'll do L prime, which is H prime, or sorry, H times L minus L. So we'll do let's do equals H times L minus L. Hit enter. We can highlight both at the same time, drag those babies down, and we get something like this. So it looks a little crazy, but let's talk about how we can actually use these values, right? So I'm gonna go ahead and just write out all these as best I can here. So we'll do 0.525. Just do the first column. Negative 0.4, negative 0.52, negative 0.05, and 0.15. And then 0, 325, 75, negative 33, 55, and 35. 33, 55, 35. All right. Now, they've done the first one for us. Let's reiterate it though. So they have the ordered pair 1 and 0.5. So they put a point at 1 and 0.5. They went to the right by 0.5, and they went up by 0, right? They did not go up because the the L prime value was 0. So then they already have another one. Okay, so they have 1.5, or we have 1.5, 0.65, which looks a little different from what they have there, but hopefully this is still kind of valid. They go, let's see if their line matches what we have. So they go to the right by about 0.525, and then the idea is to go up by 0.325. So I'm reading these values here, right? And then, so they've done that line for us, I guess. And now let's do the next one. So 1.6 and 1.25. So 1.6, 1.25, we're now like up here. And we're going, so because it's a negative H prime, it's negative 0.4, we want to go backwards by 0.4. So to the left by 0.4. So we're going over here, roughly, and then up just by 0.75, which is a lot in this scale. So we're going up really all the way to like 2 here. So that's the base. We draw a little arrow, put an arrowhead there, and that's the time 2. So I'll do like one more and then I'll wrap it up, but they want you to do it for all of them, right? So for time 3, we're going to put 0.8 and 1.65. So 0.8 and 1.65 are looking like right here. And then we're going to the left by 0.5. So we're going all the way to like 0.3, and we're going down by 0.33. So, I'm just roughly estimating here, maybe something like this. And that's for time 3. and then you would keep going along. I just realized I'm barely showing you what I'm drawing over here. Anyway, hopefully it's still caught it all. Oh, goodness. Yeah, so you'll continue to do that for time 4 and time 5. All right, finish the phase space. Yeah, okay. Using phase portraits. Okay, place a dot on the initial point. Okay, so 0.5 and 1.2, and I used my little highlighter originally to highlight that point. So at 0.5 and about 1.2, we have a dot here, and then using the arrows as a guide, sketch a solution. So sketching a solution means to start at that point and really just kind of follow these arrows around, and most likely they're going to just end up right back where they started. And so that's kind of the idea here, is you put the point on the initial condition and then you follow it around using the directions. Now, using your sketch, think about what separate graphs of H of t and L of t would look like given the initial conditions. So what they're trying to say here is going backwards on this graph. So like this graph is L and H, but now they want us to translate it to a graph of H and T, and then of L and T. And so they give you like this hint that maybe could have been worded better. Let me move my camera. They say for the first graph, start at the initial point. So start at the initial point and trace your sketch of this graph here while watching the H values change. So the idea is when you start at this point here, your initial point, we want to follow this curve around, but we'll only think about how the H values are changing, right? So like when we go down this first little slant, the H values aren't changing, but as we go across, the H values are changing. And where do the H values max out? So the H values start at the 0.5, they kind of halt for a little bit, and then they start moving, and they hit like a max H value of maybe 1.7, something like that. And then it, as it moves vertically, there's no H change, and then it keeps going around. And what does H do? It goes back from like 1.7 all the way back to 0.5. So it starts at 0.5 for a little bit, moves to 1.7, stays there for a little bit, moves back to 0.5. So we need to graph that over time, right? So stays at 0.5 for a little bit, works its way up to 1.7, works its way back down to 0.5. That's your H of t, all right? And then L of t, it's sort of the opposite. Instead of considering what H is doing, we're considering what L is doing over time as we pass around this circle here. So let's wonder if we can change colors. Let's do like a blue for L. So the L values, where do the L values start? They start at 1.2. So right here at 1.2, the L values go down, 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 and they hit kind of a minimum of 0.5. And then they halt at 0.5, and then they start going back up, 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 and they hit a max of like 1.5 or maybe like 1.6, I don't know. And then they stay there for a little bit, and then they come back down to 1.2. So they start at like 1.2, and then they go down to 0.5. So start at 1.2, and then they go down to about 0.5, and then they chill at 0.5 for a little bit, and then they start, let me think about it, they go up to about 1.6, stay there for a little bit, and then they come back down to about 1.2. So hopefully, I don't know, hopefully that makes sense. I think that makes sense. Hopefully I didn't mess that up. Let's see. So it starts at 1.2, goes down to 0.5, comes up. Yeah, why not? That looks all right. All right, hope that makes sense. Let's check out this last one here. Phase portrait applications. We're basically at the end here. It's going to be a very long video. I'm sorry. Let's jump into it. So we have A, B, and C representing L and H, L and H, L and H, describing L for lynxes, H for hares. Typically, HL is a hare and lynx predator-prey model. They say, which of the above phase portraits, A, B, or C, depicts a situation where only the lynxes eventually die out? So the key word is only. Only the lynxes will eventually die out. To die out for the lynxes means that the L values should die out all the way to a 0 value. While if it's only them that's dying out, the hares should not die out. The hares should be non-zero values, right? So we're looking at these slopes, kind of thinking about maybe like what different paths these are taking, yada yada, and thinking about which one would lead to L going to 0 but H not going to 0. So when I look at graph B, following these lines, what it looks like is that the L values, which is basically like the Y value of the graph, goes down to 0, but the H values aren't at 0. They're, this specific solution I've drawn dies out at like, it follows to like H is 1.5. So H is about 1.5 for that specific solution, right? And I'm pretty sure for any solution, it would be non-zero. H would be non-zero, but still L would be 0, right? So B is my answer there. Let's look at number 2. They say, what's the phase portrait where both lynxes and hares die out? Now, we look at graph C. No matter which route you take, all of those solutions end up with L being 0 and H being 0. So that means both lynxes and hares are dying out. Get rid of most of the sketches there. All right, number 3, where neither lynxes nor hares die out and the species coexist. So that must be graph A. An easy solution would be like this little ring here. And then even if you go a little wider, you're hoping that, these kind of just like circle back around. It's hard to tell what's going on in the x-axis, but I imagine there's arrows that just keep it flowing. Just keep it flowing in a circle, so it just keeps the lynxes and hares never dying out and just existing together, right? So I'm going to call that A. Then in phase portrait C, place a dot at 1, 1, and then they want us to do kind of the same thing we did a moment ago. So if we look at 1, 1 on this graph here, get rid of the details. 1, 1, we're looking, oh gosh, like right here. They want us to sketch a graph, right? So we'll sketch the solution. A little rough one there, but seems all right. So at 1, 1, they want us to put 2 graphs, make 2 graphs, for one for H of t and one for L of t. So it's kind of the same practice where starting at this point, what's the initial H value? The H value is 1, and then how does the H value change over time? Well, we follow it. H is getting less and less and less and less until it dies out. The hares die out all the way to 0. So the H values start at 1, and over time they're dying out pretty consistently. So I don't know if it would be something like this or something like more linear. I feel like I should know that for sure. I mean, it seems like, I guess it would be, so it dies out faster over time. So I think it would be more, let me think, I'm trying to make sense of it. I don't know. It's anything that like shows that it's starting at 1 and dying out is probably valid, so I might just leave it like that. And then we'll do the same thing for L. L again will be very similar. L starts at 1, and the Y values decrease until it dies out. So the L values will decrease until it dies out. So very similar graphs for those. Let's look at number 5 in phase portrait B. They give us 1.8 and 1.2. 1.8 and 1.2. Where is that? Like right here maybe. And we want to sketch a solution here. So we're going bam, 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 something like that. A little rough, but not too bad. So what is H doing? So H is starting at that 1.8 right here, and it backs it up until about 1.1, 1.2, but then it increases again all the way to 1.8. So we're starting at 1.8 for H, way up here. Again, it drops down to about 1.2, but then it picks it back up, back to like 1.8. So something like that. As long as it's generally the right idea, I think that's the important piece. Now for the L values, what are the L values or the Y values on this graph doing? From the start, I think they started at what, 1.2, and then they're just consistently headed south all the way to 0, right? So we're looking at like 1.2, and we're looking for something to die out over time. Hope that makes sense. Good place to stop there. That should be the end of the lab. So hope this helped your understanding of this lab and this kind of information. Thanks for working through it with me. If you have any questions, let me know.